Cascode Stage. As explained in Chapter 3, cascoding proves beneficial in increasing the voltage gain of amplifiers and the output impedance of current sources while improving the shielding as well. The invention of the cascode in the vacuum tube era, however, was motivated by the need for high frequency amplifiers with relatively high input impedance, viewed as a cascade of a common source stage and a common gate stage. A cascode circuit offers the speed of the latter by suppressing the Miller effect and the speed input impedance of the former. Let us consider the cascode in figure. First, identifying all the device capacitances at node A. CGS1 is connected to ground and CD1 to node X, and at node X, CDB1, CSB2 and CGS2 are tied to ground, and the node Y, CDB2, CE2 and CL are connected to ground. The Miller effect of CD1 is terminated by the gain from A to X. As an approximation, we use the low frequency value of this gain, which for low values of RD for negligible channel length modulation is equal to minus GM1 by GM2 plus GBM2. Thus, if M1 and M2 have roughly equal dimensions, CGD1 is multiplied by approximately 2 rather than the high voltage gain in a simple common source stage. We therefore say Miller effect is less significant in cascode amplifiers than common source stages. The pole associated with node A is estimated as omega PA is equal to 1 by RS CGS1 plus 1 plus GM1 by GM2 plus GMB2 CGD1. Figure high frequency model of a cascode stage. We can also attribute a pole to node X. The total capacitance at this node is roughly equal to 2 CGD1 plus 2 DB1 plus 2 SB2 plus 2 GD plus CGS2 plus SB2 plus CSB2 plus CGS2, giving a pole. Omega PS is equal to GM2 plus GMB2 by 2CGD1 plus CDB1 plus CSB2 plus CGS2. Finally, the output node yields a third pole. Omega Py is equal to 1 by RD CDB2 plus CL plus CDB CGD2. The relative magnitudes of three poles in a cascode circuit depend on the actual design parameters, but omega P S is typically chosen to be further from the origin than the other two. As explained in chapter, this choice plays an important role in the stability of op amps. But what if RD in figure is replaced by a current source so as to achieve a higher DC gain? We know from chapter that the impedance seen at node X reaches high values if the load impedance at the drain of M2 is large. For example, equation predicts that the port at node X may be quite lower than G M2 plus G MB2 by Cx if RD itself is the output impedance of a PMOS cascode current source. Interestingly, however, the overall transfer function is negligibly affected by this phenomenon. This can be seen by an example. If a cascode structure is used as a current source, then the variation of its output impedance with frequency is of interest. Negliging C GD1 and CY in figure A, we have Z out equal to 1 plus GM2 R02 ZX plus R02, where ZX is equal to R01 LL CX S power minus 1. Thus Z out contains a pole at R01 ZX power 1 and falls at frequencies higher than this value. Thank you.